only meaning 1,000, so there's 1,000 equivalents. Okay. So for every mole of positive ions, then you get one equivalent. If it's a positive 2 ion, then it's 2 equivalents. If it's positive 3, it's 3, simply 1. A negative 1 ion, 1 equivalent, negative 2 would be 2 equivalents, negative 3 equivalents. Okay, so that we have 1 mole of that substance. In terms of the IV bag, so we just make sure that the total of equivalents is balanced, and that would be on a paper problem because in real life they have to be balanced. It just wouldn't work. You cannot separate. Okay. When you just solve a camera, it comes up with positive and negative ions. You cannot get just as simple as table salt. Table salt is made up of positive sodium ions and negative sodium ions. So every mole of sodium ions is 1 equivalent. Every mole of chloride ions is only 1 equivalent. But you cannot add sodium without the Cl. You cannot add Cl without the sodium because it comes together as NaCl. You cannot purchase sodium ions by themselves. You cannot purchase chloride ions by themselves. They have to come with something. An example, a solution that contains 25 milliequivalents of sodium and 4 milliequivalents of potassium. So we add the two, 25 plus 4, we get a total of 29 positive milliequivalents. Well, there has to be a counteracting ion with an equal amount. So in that example, then we would get a total of 29 milliequivalents of Cl minus. So 29 positive, 29 negative. In solutions, and the assumption is always based on having an equal amount in millimoles. So your positive 1 ions, because they're positive 1, they count as 1 equivalent, per mole. Your positive 2 as 2 equivalents, positive 3 as 3. And same thing on the negative ones. And what you see here on the list are the common ions that you see in IV solutions. So IV solutions will contain a combination of these ions. Sodium, potassium, lithium, radium. On the negative side, chloride is the most common one, but you also have acetates, lactates, carbonates, phosphates. Lab tests for a patient indicate a blood calcium level of 8.9 milliequivalents. How many moles of calcium ions are in 0.5 liters of blood? So the test is milliequivalents per liter. That means the liters on the bottom. So when we multiply the volume, the liters cancel. So 0.5 liters times the concentration, 8.8 divided by 1. This is for calcium 2 ions. And so we end up with 0.0044 equivalents of calcium ions. But because of that plus 2, there's 2 equivalents for every 1 mole. So to convert it into, so there's a typo here. This should be 0.0022 moles of calcium. Equivalents cancel, leaving us with moles. If this is a plus 1, then it's a 1 to 1. Plus 2, 1 to 2. If it's a plus 3, 1 to 3 ratio. So this, whatever number this is, that's whatever the charge is. And doesn't matter if it's positive or negative. If it's negative 3, then it's conversion to use. If chloride ion is the only other ion present, what is the concentration in milliequivalents? remember it has to match. So we have 8.8, there has to be an equal amount of 8.8. But for the moles of Cl, because it's a 1, then this will be a 1-to-1 ratio. And this will be 0.0044. So we have twice the number of moles of Cl as we do calcium. Okay, and that makes sense because in the balance equation, calcium chloride is CaCl2. It's a 2-to-1 ratio. 2 moles of Cl for every 1 mole of calcium. And the calculation would show that. If it's calcium 0.022, then the Cl would be twice that value. And so you got this table in lab on Friday. And so common electrolyte concentrations and common IV bags that you will encounter. So we have normal saline. And it's called normal because it matches, and we'll see that a little bit later on. It matches what should be normal for the body, which is what's called an isotonic solution. It has the same ionic concentration of electrolytes as blood plasma has, basically. So, and that's equivalent to 0.9% HCl. So it's 154 on the positive side and 154 on the negative side. So it's just NaCl. Notice that says replaces fluid loss. So in the case of dehydration, when there is no, you have dehydration, but your electrolyte levels are normal, then you will use normal saline. Because it's isotonic, matches what's already in the body, it's used for all other things. So a lot of times you'll be using normal saline as a carrier for IV drugs. So piggyback that drug on the IV, so the drug doesn't go to the system. Okay. Then when you need to replace particular electrolytes along with volume, then you would use a lactated regular solution, and so you'll notice that the amount of sodium is a little bit less. That contains potassium and calcium. Again, that's when those levels are low. Potassium is very, very important for cardiac function. So when you look at these electrolyte levels, say that potassium levels are out of normal limits between sodium, potassium, and calcium, that potassium is important. More important than the other two. And that's the first one that should be addressed. And then as you see on the bottom, then you have chloride and lactate ions, and that's where it says lactate in regular solution. So that contains some of the lactate ions. And this lactate comes in the form of sodium lactate. So when it gets dissolved in the IV solution, it comes with the sodium. Either way, 137 positive, 137 negative. Maintenance solution. Okay. You go to you're dehydrated, you end up at the hospital, you get back to normal. Once you're back to normal, but they're changing other things, then that's when you get the maintenance solution. Okay, you do not want to keep getting sodium. And so that's when you're already stabilized. But there's other issues outside of hydration and electrolyte balance, so that's when you would get a maintenance solution. You can notice that the sodium levels are a little bit lower. And then once again, 75 and 75, notice that the total load is less than what is normal. Okay, because this is just supposed to be maintenance. That scenario. And then if your electrolytes, in addition to potassium and calcium, are low, okay, some of these in here, then you would end up with what's known as a replacement solution. And on the negative ions, usually Cl is the highest one, okay, it's in decimal cases, but here we have also acetate solution. Kind of like vinegar, acetic acid, or acetate comes in the form. And then positive and negative sources in that as well. Cases. So here we're matching the charge. So it's 1 mole and 3, so 1 times 3 is 3. Got 3 equivalents. 2.5 moles, the charge is at 2, so 2.5 times 2 gives us 5. So to get the number of equivalents, it's the number of moles times the charge. In the previous example, we were working backwards. We went from equivalents to moles. So you take the equivalents and divide it by the charge. And so for calcium, that's why we divided by 2 in the previous example. Here then we multiply. Now every bottle contains sodium chloride, and the sodium is 34, and it's plus 1. So the Cl has to match that. So it's also going to be 34.
Because you times, okay.
Not all ionic compounds are soluble. Some compounds are not soluble. Gout, primarily affects adult men over the age of 40. Lack of gout may occur when the concentration of uric acid in blood plasma exceeds its solubility of 7 milligrams per 100 mL. Even when we do have soluble salts, there's a limit to how much it will dissolve. Okay, so you add salt to water, it dissolves, you keep adding, at some point it won't dissolve it. Well, in the body.
That's too much, so.
And so gout then occurs when uric acid concentrations go above 7 milligrams. And what happens is that it begins to precipitate. That excess forms crystals, forms a salt. Okay. Solubility is dynamic. So you add more salt, and it just seems to clump at the bottom. Technically, it's not clumping. As you keep stirring, you keep dissolving. But salt that was already dissolved undissolves.
Oh.
So the crystals that you see on the bottom, they're not the same crystals.
Wow.
They're disappearing and reappearing.
So is that the same with sugar or no?
Yes.
Wow, that's
With
great.
any solid that is soluble. If you're above the solubility limit, then you're in a process of dynamic equilibrium.
Wow.
It's dissolving but precipitating. Salts precipitating. Salts and precipitating.
But why equilibrium if it's not equal?
It keeps it trying to get
The-
equal.
The rate, what's equal is not the amounts, but the rate at which it dissolves and precipitates. It's the speed.
So that the dynamic is.
Dynamic means that it goes up.
Goes up.
It
Continuous.
seems like it's static. And so to I'm using this as an example. So 7 milligrams in 100 mL. So say we have 100 mL of water. Well, blood. And we put 10 milligrams of citric uric acid. But the solubility is 7. So that means that over here on the bottom, we would have 3 milligrams of the acid, and then dissolved in here is 7 milligrams of the uric acid. So that's the salt, that's salt. As we look at it, it seems like nothing is happening. Okay? But it's at an equilibrium. That equilibrium though means that internally at the molecular level, these crystals, they're still dissolving. But for every crystal that dissolves, one that was already here precipitates back into a solid state.
Wow.
The equilibrium part, the equal part, is at the speed at which this happens. It's happening at the same rate. That's
So it's always 7 and that's always 3. They just kind of switch on which one.
Right.
Okay.
right. So you have a at a Sun State or whatever, and you have a roller coaster right that's popular. Okay, and inside that roller coaster, 16 people are riding, and you have a line with 42 people in line. Okay. Now, in order to get to an equilibrium, we're closing the whole thing. We're closing the ride, and we're not letting any new people in line, but the ride's still on. When these 16 riders finish, they get back in line. And the ones that are in front of this line, they get to ride. But it's just going in circles. So if you're far away, it's like, well, the line's not moving because it's always the same length. But it's not the same people. And that's what an equilibrium is. It gives the appearance that nothing is happening, but it is.
That's
At the
awesome.
same speed.
And so that excess precipitates, and for ionic compounds, it forms, all ionic compounds, when they're in a solid state, they make crystals. Now, there's different shapes of crystals. Some are little round, some are cubic, rectangular. Some are needle-like. And uric acid happens to have needle-like crystals.
I lost the thread of the conversation. Could you rephrase what you said?
Sorry.
And so those crystals precipitate in the joints. And basically you have these needles in the joints, and it becomes very painful. And then as the more needles aggregate, then movement of the joints begins to decrease. And you can move the joints less and less. And so the idea is to redissolve those crystals, but there's not a very good compound to do that. Like once it's in the solid state, it's difficult to get it there. Diet and all that helps with the excess, with keeping that excess below those levels. So this solubility right here refers to this. The maximum amount of a solute that will dissolve in a given amount of solvent. And typical way of denoting solubility is like grams of solute over 100 grams of water. Keeping in mind that 100 grams of water is 100 mLs. Density of water is 1 to 1. So 100 grams or 100 mLs is the same. Then we have a series of scenarios. In an unsaturated solution, then we have less than the maximum amount. So everything dissolves, and you can still have room to add a little bit more. Okay. Now, keep in mind though that sometimes it takes a while for something to dissolve. It's not instant. So you need to stir, and sometimes you need to stir for several minutes. So when sugar is very, very soluble in water, when you add sugar to iced tea, it clumps at the bottom because you only stir for like 30 seconds. Now, if you have the time, in your meal, and you stir it for 5 minutes, all of that salt, all of that sugar is at the bottom of the salt. But, you want to have your meal, you want to drink your tea, so you're not going to be there to that.
So it's
Just
not
keep
'cause
adding
it's,
more
I
sugar.
always thought it was because it was cold.
Well, it reduces the solubility. But even in cold water, sugar is still very, very soluble. So you can get it to do that. Soluble enough, when you make lemonade and you put it in the fridge, the salt doesn't precipitate, doesn't clump at the bottom. Which it would for other salts.
Why? Because of the acid?
As you drop, when you put it in the fridge, it drops the temperature, it lowers the solubility. So, if it's unsaturated, you have less. If it's saturated, then that's when we have this scenario. Okay, when you reset equilibrium. So in a saturated solution, you have the maximum amount of solute that can dissolve. But the only way to make sure that it's saturated, okay, we need to make sure that there's a solid. And with continuous stirring, no more of it appears to dissolve. Then we know that the liquid port is saturated, because this is appearing there. So we cannot make sure it's this until we have this equilibrium between the undissolved one, the crystals, and the one that did dissolve. Because you're not gonna get it exactly at the 7 or the value. Doesn't happen. So, unsaturated, here, the liquid layer is the one that's saturated. Okay, that's the saturated part right here. The liquid over has the maximum. So if all of it disappears, it's unsaturated. If you end up with some of it at the bottom, then the liquid portion is saturated. At 40 degrees Celsius, the solubility of PBr is 80 grams per 100 grams of water. Identify the following solutions as either saturated or unsaturated. If you do 80 divided by 100, that's 0.8. So basically, 0.8 grams of the solute for every 1 gram of water. Okay. That's the solubility. So we have 60 and 100. Well, that's 0.6, that's less. So that's unsaturated. If we have 200 over 200, then that's 2. 2 is bigger than 0.8. So this one here will be saturated because we have an excess on the bottom. 25 divided by 50, that's 0.5. 0.5 is less than 0.8, so it's unsaturated. So when you divide this, 0.8, that's like the magic number for that. Anything above 0.8, it's saturated. Anything below, unsaturated. And so right now we're talking about the ice and iced tea. Temperature affects the solubility of a solid. For solids and liquids, then the rule of thumb is as you increase the temperature, you increase the solubility. And as a rule of thumb, there are a handful of salts whose solubility decreases. But most of them will increase. They don't all increase by the same amount. Table salt increases very little. In that whole range, it goes from about 38 up to 40. So it's not a big difference. Okay. Sugar, though, it's a big difference in solubility. At the freezing point, okay, so right where you have liquid water at where it's starting to freeze, you can dissolve about 50 grams of sugar. That's half the amount in water. Okay, when you're warming up water, where's 100? 100 right here. So 40 degrees Celsius. And so 4 times 1 is 80. That was 32. So about 112, let's say 110. Okay. And when it's about 110, you can dissolve more than twice the amount. More than the amount of water that you have. So this 100 point, at that point you could even correction at 130. So you did have more sugar than you do water, and it will still dissolve. You can take 130 grams of sugar, dissolve it in 100 grams of water, and it will still dissolve. You may have to stir for like 10 minutes, but it will dissolve. And so you notice so the solubility at 0 degrees Celsius, it's still about 50 grams, 50 grams and 100 grams of water, that's a lot. So if you're 2 quarts of lemonade, so that's 2,000 grams. So 1,000 grams, 2 pounds. Okay, so you can take 2 pounds of sugar put them in a 2-quart container of water, and all of it should dissolve, even if you have ice in there. Now, like I said, it's gonna take a while, you need to stir, but those 2 pounds will dissolve. You know, you go to the store and there's that big bag, you can empty that whole big bag into a quart of dissolve. For gases, it's the opposite. Increase the temperature, solubility of gases decreases. So, like on a carbonated drink, if it's warm, it has less CO2, it goes flat. If it's cold, then more CO2 is retained, it tastes better. So, for warm drinks, so not goes into CO2. That's true for any gas. As you increase the temperature, then the solubility of gases decreases. In terms of global warming, then as the average temperature on Earth rise, so do the average temperatures in water systems, oceans, rivers, lakes. That means that the amount of oxygen that is present there decreases. So if there's less oxygen, then whatever marine or aquatic life that depends on those amounts of oxygen, then are affected by it. As you decrease the amount of O2, then there's also the risk of anaerobic bacteria increase. That's bacteria that does not need oxygen, and that tends to be acid, at least for us. In the environment. But it's not the kind of stuff that we tend to like or enjoy. It can be detrimental to us. Why could a bottle of carbonated drink possibly burst when it is left out in the hot sun? Well, as the temperature is increasing, the CO2 that dissolves, and that's carbon monoxide, but this decreasing line. So whatever amount decreases, that's now in that very little empty space that the Coke has. And there's not a lot of room for gas in. So it needs to go somewhere. Next one.
Oh.
In water that's too warm, there's oxygen. No oxygen, no fish.
So it decreases the space because it increases the solubility, everything like kind of, right? So it decreases the space.
The bowl.
Do you get what I'm saying?
So you have this amount of space here.
Yeah. And then as it starts dissolving more of whatever's in there, you're losing space. Or am I thinking about it incorrectly?
The CO2 that's in here
Yeah.
is now in that space right here.
Oh, wait, I am thinking about it wrong.
And it starts increasing the pressure because it doesn't want to be the liquid. It's undissolving as it warms up.
Oh, it's undissolving.
So it goes to that whatever little space there is. The warmer it gets, the more CO2 is in there, not in the water. Well, at some point, that seal is going to break. It's going to burst. Shaking it does the same thing. That's why shake a soda and then you open it in, because that shaking it disturbs the CO2. Tapping doesn't do anything. So you drop the soda, you pick it up, and shoot. Then you do this. It doesn't help. Okay. Put it in the fridge, put it in the freezer. 5 minutes, 10 minutes. Drops the temperature, slows down the molecules, some of them go back. Take it out and carefully open it. The one as well.
So the fish die too for that same reason because they
But instead of the CO2, it's the oxygen.
Yeah.
The oxygen is leaving the water.
the water
Yes.
or them? The water?
So there's oxygen in water,
Okay.
and fish need that oxygen to live.
Yeah.
But as the temperatures increase, the amount of oxygen that's there decreases.
Oh.
So because there's less oxygen,
In the water. Decreases. Oh.
and some animal life, or just life in general, are more so susceptible to small changes in oxygen than others. Okay. And typically the smaller the animal, the more susceptible it is to those water changes. So on our size, it's not as critical. And that's why you can go and climb a mountain. You may feel tired, but you're not going to die just because you're going to decide to take a hike, right? Even though there's less oxygen. Now, the difference is very, very large, then yes, the body needs to acclimate. Okay. But for certain fish, and in your size, then smaller amounts are more critical. And then Kendrick's slide just tells us that it's for pressure and gases and liquids. At a higher pressure, then more gas dissolves in the liquid. So if you increase the temperature, you get less gas. If you increase the pressure, you get more gas. So at higher pressures, you can get more gas in the liquid. And same thing for the carbonated drink. It's under pressure, so you get more CO2 in there. So it's pressurized inside. When you open it, the pressure drops and some of that CO2 comes out.
So you said an increase in temperature, there is less gas.
Increase in pressure, there's more gas. So here in terms of Henry's law, when you go diving, then the solubility, and I think I mentioned this in the lesson. The solubility of gases and liquids increases, and blood is a liquid. So as the deeper you go in the dive, then more air gets dissolved in the blood. Okay, oxygen is not a problem because oxygen, believe it or not, is not as soluble as nitrogen in water. Nitrogen is a lot more soluble. As you go deeper, then more nitrogen gets dissolved in the blood, and the nitrogen really depends on what you do. At least oxygen goes to the tissues and gets used up, but nitrogen is not being used up. When you come back up, then the pressure decreases, the nitrogen wants to come out. And the same thing that happens in a soda can, then that happens in the blood. That's the effect of basically bubbles start to form when nitrogen starts bubbling out of the blood. Not in a dramatic fashion like that, but as it starts coming out, it causes what are called the bends. And it's very painful, and the body starts to contort. You have no control over it. And that occurs when too much nitrogen is in the blood, and then it starts to bubble up. And it occurs that. And so, depending on the type of diving that you're doing, the air in a tank gets replaced. That nitrogen gets replaced by helium, which is less soluble than nitrogen, less soluble than oxygen. So, and you end up with an oxygen-helium mixture. If you go even deeper than that, then it doesn't matter what the gas mixture is, you have to decompress. Basically, as you're diving back up, then you have to wait. There's limits. So you have like how devices that tell you how deep you are, and then you can go up, like 20, 30 feet. Then you have to stay in that area for several minutes, and then you have to go back up.
Because something happens in your brain, right? Other than the movie.
And that pressure begins to accumulate. That excessive pressure then can cause an aneurysm. And then for really, really deep, like submarine maintenance type of diving, that you need a chamber. Which basically you have to go, before you're even up, you're put into, you wear a special pressurized suits. You may have seen some of these sort of big metal things. Inside that pressurized shoes, you go into a pressurized room. That room matches the pressure of the suit, so you can take off the suit, but then you have to stay in that room for a day, maybe two. If you go vacationing, if you go to the beach, you're going to go scuba diving, do not fly, do not go scuba diving and then fly the next day. You need more time to decompress. So if you're gonna do scuba diving on a trip, do it at the beginning of your trip, not towards the end of the trip. If you're flying there or not. Because that, at the altitude of the plane, even though inside of the plane is pressurized, that pressure is not matching ground levels. If it's too low, then you'll get the bends. In very extreme cases, they can lead to death. You can kill somebody by injecting air into a vein, to an artery. You take about 6 Cs of air. That will probably do it. That's why when they're setting up IVs, they'll tip it, so you get that air bubble, and then squeeze it gets them out, so you get all of the air. All right, so not all ionic samples are solubles. Okay. Anything that contains nitrates and acetates is soluble. Doesn't matter what the positive ion is. So those are always soluble.
Just those ones, or just those? That's just an example.
Just those, no, just those.
Yeah. Okay. So always.
Obviously, it doesn't matter what the positive ion is. Chlorides, bromides, and iodides, they're almost always soluble. But there's 3 exceptions. And they're combined with silver, lead, and mercury. Soluble with low group 1, soluble with low group 2, soluble with almost all transition metals. So silver chloride, not soluble, silver iodide, not soluble, silver bromide, not soluble, lead to chloride, lead to bromide, lead to iodide. They will dissolve. And this is like germs, like you put a rock in water, nothing happens. Okay. Then sulfates. They're usually soluble, but we do have a couple more exceptions. From group 2, calcium, strontium, and barium. Okay, so these 3 are from group 2. And from the transition metals, lead and mercury. Where those sulfates are not soluble. Hydroxides, which are the strong your bases, what your bases form, they're soluble. The top 2. The soluble hydroxides are the strong bases, which are your group 1, and calcium, barium, and strontium from group 2. So those hydroxides do dissolve, all the other ones do not. And then carbonates and phosphates, soluble in group 1, but not soluble everywhere else. So this right here, we're soluble all across, those are these right here. These are your group 1 metals, but in addition to group 1 though, we do have ammonium. So here, we also need to include Anything with sodium is always soluble, anything with potassium, always soluble. And you'll notice all in terms of the body, ideal solutions. As you notice, see, sodium, potassium, magnesium, calcium are the ones that are almost always soluble. Okay, there are some exceptions with calcium and sulfate. So when you mix things that are soluble, there's a risk of having ions that combine to make something that is not soluble. Okay. So take here PbI2. So say we have a solution that contains lead nitrate.
Lead nitrate?
Well, technically lead 2 nitrate. So anything with a nitrate is always soluble. So you have lead 2 nitrate, it's a salt, put in water, stir it, it dissolves. Then we take sodium iodide. Anything with sodium is soluble. So that solution contains the sodium and the iodide ions. And then you mix the 2 solutions. As you mix the 2 solutions, these run into each other. That runs into that. And this combination, we have I minus with lead, that's not soluble. So you start making a precipitate. You start forming the salt, the crystals. Now because it's starting ion molecule per molecule and per ion, they're very fine crystals, and it looks like a very fine powder, it looks cloudy. But then give it time, and then they start setting on the bottom, starts getting very red. But it forms what's called a precipitate. Okay, so you have to worry about precipitate formation when you're mixing different ionic solutions. In terms of IVs, certain drug combinations form precipitates. And so certain combinations cannot be put together in a single IV. Because when you're putting in the medication now, there's a lot of solid in there, and you don't want to put solids into the bloodstream. It clogs the pipes. You have a heart attack, like liver. It's a pretty quick way to block blood flow. On the higher danger end, then you're talking heart attack. On the lower end, you're talking tissue death because of lack of blood. So blood flows into that area. So you have to worry about. So there's these, your drug books or your drug apps will give you contraindications in terms of medication that should be given together. Some of those contraindications is because of precipitates. It's not the only one. In terms of subcut, we'll typically see it in IV, but if you don't know, if you're unsure, as you're putting it in there and keeping an eye on it, if you see any form of cloudiness, then stop that.
Yeah.
So sulfates are soluble unless they're combined with barium, as we said here, calcium, strontium, and then barium sulfate. It's not soluble, it won't dissolve. But it makes a very nice white powder that absorbs radiation very nicely. So it gives a good contrast in X-rays and with, it's either CT or PET scans. One of those two. Barium sulfate kind of looks pretty good. But typically used for X-ray, but it is also used for some CAT scans or PET scans, I can remember. Barium sulfate, on a side note though, it's a white powder. That's the definition of what white color is supposed to be. So in areas of colorimetry, where like ours and stuff, and you have to match colors, then barium sulfate is the reference for what white is supposed to be. We may not see it as what we think is white, because we're biased towards the blue part of the spectrum. Things with hints of blue, we think it's whiter. Which is kind of how we've been trained with emissions and things like that. I don't know if you've heard that some LED lights have a blue light. If you have some tablets, it'll tell you if you want to control the blue light because it'll keep you awake. And the setup is because we've been trained towards that spectrum.
Is that because of electronics?
Yeah, it's not something that happened before, like the 1960s, 40s. Kind of originated. Really from the 80s. Because even the old solid color televisions were not effective. So it's more when, and then as we said before, for those things that are soluble, there is a limit to how soluble they are. Then usually we get those limits in terms of grams per ml. There's other ways that you can represent solubility, mass per volume, as opposed to mass per mass. In the case of liquids in liquids, then we have volume by volume, and that's for, like, say, your spirits. So something that's 80 proof is 40% by volume. That's 40 mLs of alcohol in every 100 mLs of the drink. So alcoholic drinks and your spirits are usually how much alcohol in 100 mLs of that particular. And then molarity, which we use for moles, but we're not going to worry about molarity. So prediction predict the atomic temperature for soluble or insoluble. So still sulfites in here. Cadmium is a transition metal, so sulfites with transition metals are not going to be soluble. For B, anything with sodium, it's always soluble, doesn't matter what it is. So B is soluble. Iodide is soluble unless you're combining it with one of these guys. So we are combining it with lead, so not soluble. And anything that has nitrate, NO3, it's always soluble no matter what. So not soluble, soluble, not soluble. We won't worry about it. Just remember that when you make solutions, when you make solutions, then you need to consider the combination of ions from one with ions of the other. Okay, and that occurs when you're mixing stuff. And one of those combinations must be a precipitate. And that's what you have to worry about. I'm gonna skip the math and dilutions. Just gonna skip to the formula. I think you may see that formula. What's that test that you have to take?
Hesse. Well, some of us take the T's. It depends on where we're going.
So I think the dilution formula may be. But it's a pretty simple formula. here you see a C1, B1, C2, B2, you may see it as M1, B1, C2, B2, doesn't matter, but there's always a set. C is concentration, and B is the volume. So you're always solving for one of these two. Okay. Either for C or D, whichever one you're solving for. That's what you do. You divide by the other component on the other side. In problems, the word of will connect the set. 100 mLs of something. That's a set. A 1-1 set or a 2-2 set. Doesn't matter. So the word of will connect the two terms together. So either we're trying to find out how much something got diluted and what the new concentration is, or how much volume we need to add to dilute something to a given concentration. So, what is the final concentration with 0.5 liters of 6 more HCl? It's diluted to a final volume of 1. Whatever the word of is connecting, that's the set. So you multiply those two and divide by whatever else you have. So 0.5 times 6, that's 3. 3 divided by 1 is 3. So we end up with a concentration of 3 more. I'm not sure.
I'm pretty sure, because we're not gonna, this is for the
I
Hesse.
know for the NCLEX, you're not getting the point.
No.
Yeah, but by then, you know it.
No, but in NCLEX, they ask you like clinical questions. They don't ask you like chemistry. We're gonna need this for the Hesse.
Well, no, but in terms like this, in terms of medication dosages.
Oh, you have to figure them out.
When a doctor orders a particular, and you did,
Yeah, in lab, like the
in
second.
the lab, I think there were a couple
Oh,
of these
yeah.
that you should that handbook that I gave you.
Yeah.
So for IV bags, then it's when you need to know how much to put in the bag for one. Yeah.
So it's just really knowing the formulas, but you will always be given part of the problem.
But like, this is always the word of. And the word of in math means to multiply. The word is means equals, but means to multiply. So 25 times 14 divided by 2. 14 divided by 2, 7. 7 times 25, so that's 7 quarters. So that's $1.75.
What confuses me is the canceling out.
Solute is added to water, and it doesn't matter if it's water, to any solid. When the solute is added to a solid, series of physical properties changes. One of them is vapor pressure, but the important ones that kind of I would like you to remember is that the boiling point increases and the freezing point decreases. If we're at sea level where water boils at 100 and freezes at 0, if you add salt to it, then it boils above 100 and freezes below 0. Increases the boiling point, decreases the melting. When you add antifreeze, that's linked glycol, to your radiator,